Hello, this video will review momentum conservation and collision. We let's just the highlights of it. Let's look at it. We want to distinguish between one-dimensional case and two-dimensional case. So, first thing to do is to set it up. So this is you want to always draw a picture like this, where you have some drawing which says which axis you're going to use and what the balls or objects colliding with the velocities will look like. So in one dimension, everything will be along the one axis. It might be this thing is pointing to the right and this thing pointing to the left, or vice or both pointing to the right or both pointing to the left, and so you need to make sure that you have the right setup here. And here you might know one of them going which way, but the other one may not know. But so you can take it, assume something here, which later you can correct. Okay. So we need axis because the momentum conservation is a vector equation, and so when we have one-dimensional case, we have a vector equation along the x-axis, for instance. So we will need to work out the component of the velocities. If these are the speeds, then maybe positive, negative, you need to work out which is positive, which is negative, both positive, both negative. And similarly here, you might just end up with a symbol here, and once you work it out, here is the momentum conservation along the x-axis, and then in terms of the full formula, it looks like this. We're going to have an example of this. In two-dimensional case, you have the setup is a little bit more complicated, and there you need both x and y axis. If this whole thing is happening in xy plane, what is the situation for before and what are the symbols for the after? You might be working with the component names rather than angles and speed. Okay, so you'll have to work out, once you have that, you have to work out what the components are. So we'll go to the velocity v1, I'll get the x component and y component. v2 similarly work out x and y component. Similarly work out x and y for this guy and x and y for this guy. And once I have these components, I can write the momentum conservation, which is a vector equation now. So there's a mistake here, not x there. This is vector. This is vector, which is it's got both x and y here, both x and y here. And so this is along the x-axis. So all of them are the x, 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 so the x components. And this is along the y-axis. This will all be the y's. So as if there are two one-dimensional collisions, one along the x, one along the y. And the net effect is that collision over there. Okay, so let's look at an example of a one-dimensional collision, a numerical example. So here is an example. If you want to work it out yourself, go ahead, pause the video and work it out. I'm going to work out a solution right in front here. So let's see. We are going to set it up first thing. So it seems like a ball A is moving to the right and ball B is moving to the left, and maybe x-axis is that way. So this is, we can just say 1 and this is 2. So we have a v1x will be plus 20 meter per second, and v2x will be minus 10 meter per second, because this x-axis pointed that way and this is going that way. So that's what I was saying, you have to work this out first. You have to work this out first. Always work this out first. So I caught this minus sign here, right? So this is the before situation, and in the after situation, it says the second ball B, goes this way 2 meters per second. That's the ball B. And ball A, I don't know what's going to happen to ball A. So I just work with the components now. This will be, maybe just assume it goes with the speed v over here. And x-axis, you'll have to use the same x direction. So v2 x is given as plus 2 meters per second, but v1 x is unknown. So if this is flips, if I'm using this direction and I find this to be negative, then actually it is in that direction. So that will be the way it will work. So, well, now we have complete information. We can write the conservation of momentum. So 20 times 1, so, and then the other one is 3, plus 3 times minus 10, which will be minus 30 on the left side. And for after, this is the after, so the after situation will be, this is 1 times v. I don't know if it's going to be plus or minus at this point, plus 3 times 2. Okay, so if we solve for v, this side is minus 10 and this is 6, so on the other side divide by 1, so v will be minus 16 meters per second. So this is minus. What we found out is v1x. So this is actually v1x. Let's call it primes. So that I'm consistent with the previous notation. So v1x prime is minus 16 meters per second. Well, if this is x component, so the speed will be 16 meters per second and the direction will be to the left. So that will be the answer. And how to answer this, is it elastic or not? So we have to check if the kinetic energy before is kinetic energy total before equal to kinetic energy total after. So you have to compute that and you have to compute that. Now you know all the speeds and check. I'm going to leave this as an exercise for you to check. You will find that not elastic. So this is for you to check. So for instance, I will have half times 1 kilogram, so 20 square, plus half times 3 kilogram times 10 square. I don't need to have a minus there because the speed. Is this equal to half times 1 kilogram, I just figured out 16 square, plus half times 3 kilogram times 2 square. So you have to add these guys and these guys, see if they're equal to each other. They're not in this case. Okay. The second problem is, it says forget about the data given, this data of the after the collision over there. Okay, that was the case if it was some kind of inelastic. Suppose it was elastic. What would be the velocities after? So this 2 meters per second doesn't apply anymore. So we are going to work out this problem. So let's see what we get. Okay. So here we're going to have two conservations here. One is momentum and another one is kinetic energy. So there are two conservation equations. So setup is very similar. So this is ball 1 with 20 meters per second and ball 2 10 meters per second. this is the before, but the after I don't know. This is not known here. This is 1 and 2. So this, maybe you can just take it both to the right, okay, and see, work out the answer. So I usually like to use simpler symbols rather than primes, etc., just for the sake of algebra. So this is the after. So if I do this, and you can set it up and things like that, and you know from here you are going to get 1 times 20 just like before, plus 3 times minus 10 for the momentum, and this is going to be 1 times u plus 3, m equals to 3 kilogram here and m equals to 1 here, so 3v. So this is one equation, and then you're going to have kinetic energy conservation. So I got two unknowns here. You can see kinetic energy conservation will be half times 1 times 20 square plus half times 3 times 10 square. So this is kinetic before, and then half times 1 times u square plus half times 3 times v square. So you got two equations and two unknowns. Let's simplify them just so that we can work with our simpler equations. It's got u plus 3v equals to minus 10. So that's one equation I got. And this one you can see that this half all go away from each of those terms. And so this 400, you have a 400 plus 300. So you have a 700 here. And then you have a u square plus 3v square is 700. Okay, so how do I solve these equations? You see, okay, if I probably there are several ways of doing it. Let's do one way. Let's make this 3v equals to minus 10 minus u. So if I were to square both sides, no, I'm saying solve for say 3v, I can kind of convert this. Let's start over again. So I'm going to solve this for u, minus 10 minus 3v, and then plug this in here and see what comes up. So minus 10 minus 3v square plus 3v square equals 700. And this is just equation and one unknown. It's a quadratic equation. So let's expand this, and 130, and that's going to be plus 60v plus 9v square plus 3v square equals 700. So these guys add up, and I get 12v square plus 60v minus 600. 700 comes over here, 600 equal to 0. You can see I can divide by 12 everywhere, so I get a v square plus 5v minus 50 equal to 0. So the v is 1 over 2, 5 minus 5 plus the minus square root of 5 square, minus with a minus 4 times 50. That's, so this is 200 and this is 25. So this is 225, and that's square root of 225 is 15. So v is equal to half minus 5 plus or minus 15. So this is equal to, if I use a plus here, then I get a 10, so it's 5 meter per second. Or if I do both minus, then I have 20 over 10 is 20 over 2 is minus 10 meter per second. So this is, it's saying that if it turns around, then it's 5 meter per second, and if it goes on the other side, if the v is not this way, if it's this way, then it's 5 meter per second. If v is the other way, it's minus 10 meter per second. Let's see if it makes sense. All right, so one of these will definitely make sense. So when v is 5 meter per second, I can use the u will be minus 10 minus 3 times 5 is 15 minus 25 meter per second. So it's saying that ball A returns with 25 meter per second and ball B goes with 5 meter per second. So this is one situation. That's one situation. So that's one situation. The second situation is with a 10 meter per second. V is minus 10 meter per second. Then U is minus 10 minus 3 to minus 10 is plus 20 meter per second. He's saying that A, after the collision, goes through B and is moving with 20 meter per second, and the B is actually moving minus 10 meter per second. So this is actually unrealistic, that B goes right through it. Unrealistic. So it will seem that this is a B should return back. So the answer I would get is VA prime is 25 meter per second returns. VB prime is 5 meter per second and it reverses direction. So that's if it was elastic. We already know if it's not elastic, then there is a situation in which it just this is not 5 but 2 meter per second. Okay, so this is how you do elastic and inelastic collisions, and this you do any collision in one dimension will be like that, but the elastic collision in one dimension will have momentum conservation and kinetic energy conservation, and you have to work with these through, and you have to work out if something is unrealistic or realistic from the answer you get. You usually get two answers, and one of them is some it usually looks like this, and so you pick the answer that makes physical sense. I'm going to stop here.